do these reactions. We're going to do these reactions as demo reactions. So I'll do these at some point. But all of these are double replacement reactions. So if I take lead 2 acetate and sodium carbonate, what would I make? So what you do is you swap the ions. So we could swap the anions. You'd make lead 2 carbonate and sodium acetate. So we just swap the anions. So lead goes with carbonate, sodium goes with acetate. Lead 2 carbonate's a precipitate. That should precipitate out. But we'll take a look at it. How about lead 2 acetate with sulfuric acid? What would we form here? Yeah, lead 2 sulfate, good. And? Acetic acid. Lead 2 acetate with sodium hydroxide? Lead 2 hydroxide and sodium acetate. Lead 2 acetate with aqueous ammonia. Lead 2 hydroxide and ammonium acetate. This one's a little bit tricky because ammonia, what it does is it supplies a little bit of hydroxide in the form of ammonium hydroxide. So when we have aqueous ammonia, it's a weak base. Weak base is partially hydrolyzed water. And they're going to partially hydrolyze water to produce ammonium hydroxide. So when I see aqueous ammonia in a double replacement, I think ammonium hydroxide. However, I don't write ammonium hydroxide. Even though it is ammonium hydroxide that's reacting, when you go buy the chemical, you're going to buy aqueous ammonia because it's only about 1% hydrolyzed. Well, 1% hydrolyzed is enough to precipitate out lead 2 hydroxide. And so it's like 99% ammonia, 1% ammonium hydroxide. So if you go to the store and you ask for ammonium hydroxide, you're only going to get 1%. The rest is ammonia. And so they just call it aqueous ammonia. It's more accurate that way. Does that make sense? So in the equation, though, in the equation, we write the equations for the chemicals that we purchase. So we don't write, even though it is ammonium hydroxide, we don't write ammonium hydroxide. We're just going to write, you know, lead 2 acetate plus aqueous ammonia and water. And that's going to do it. And so we'll look at those later. Today we're going to do a different experiment. And you guys are going to do it. You can work in groups of 1, 2, or 3. And we're going to run through some redox. These are metathesis or double replacement reactions. When you form a precipitate, you know, there's not a huge amount of energy that's changed. And so precipitation, gas formation could be a little bit violent, you know, because you could have splattering and effervescence, but it's not terribly violent. And stronger to weaker acid, you know, some heat can be generated, and that could cause some heat burns, but normally they're pretty mild. In redox, it's much more significant, you know, the energies that are involved in redox reactions. So redox reactions are more dangerous in the sense that we have to worry about potential hazards if a large amount of energy is produced in a short amount of time. And so let's take a look at our redox chart here. I forgot to post the clean copy of the redox. This is redox and acid-base chart. Yeah, shoot. I wonder if I could. Delete these. Well, go over here. Need to get rid of all these. Well, anyway, what we're going to do is we're going to look at these species over here. So the first thing we're going to do is we're just going to look at the oxidizers and read their names. So let's go down the list of oxidizers here. At the top is F2. What do we call that? These are the oxidizers over here on the left side. And one thing oxidizers do is they take electrons. So F2 wants to take 2 electrons. And I call it the top because F2 is, you should memorize that as the what?
That's fluorine.
Yeah, F2 fluorine is what?
The strongest oxidizer.
Yeah, the strongest oxidizer. That was your assignment last week, is to memorize F2 and the other one?
Lithium.
Lithium, which was the strongest reducer. Yeah. And so we know F fluorine is the strongest oxidizer, wants 2 electrons to make fluoride. Now, fluorine's a powerful, in fact, most of the elements on the right side of the periodic table, except the noble gases. The noble gases are happy as is. So to the right of fluorine is neon. Neon is extremely stable. And what fluorine wants to do is it wants to be like neon, right? Fluorine has 9 electrons each. And if it can gain 1 more electrons, then it has 10 electrons, like neon. And so here, if I have 2 fluorines, each one gains 1 electron. We'll have fluorides, which are like neon. Isoelectronic, we call it. Isoelectronic means the same number of electrons as neon. And then fluorine is happy as fluoride in a redox sense. Fluoride is reactive in a metathesis sense. But here, fluorine wants 2 electrons, and how badly does it want? Well, it's the strongest oxidizer. And so we call fluorine electron poor. It's not happy with the 9 electrons it has. It wants 10 electrons. And so fluorine is the most electron poor species on this chart here. Oxygen wants 2 electrons each. You know, if we look at oxygen, it has 8 electrons. To be like neon, it needs 2 more electrons, and that will give it 10 electrons. So this oxygen, though, is ozone here, and actually, this one is deficient in electrons. Actually, ozone is a kind of a weird species. When we look at the Lewis structure, and it doesn't go all the way to oxide. Oxygen would like to go to oxide. Oxide is O with a 2- charge. This is O with 0 charge. However, if we have 3, this is elemental ozone, so all the oxidation states are all 0 here. But when we look at the Lewis structure, it's not all 0. You know, the average oxidation state is 0, and so this is why I do oxidation states based on Lewis structures, because it gives us more insight into what's going on. So normally we follow the rules. The rules say elements in elemental form have an oxidation state of 0, but I don't want the average. I want the individual oxidation states. And so ozone has an interesting Lewis structure here. Let's take a look. You know, each oxygen has how many electrons? 6 normal. And so that gives us 18 electrons here that we have to put in a structure. Now, ozone is going to have 3 oxygens bonded. You know, there are different ways we could bond it. We can bond it in a chain like this, or we can bond it in a ring like this. This ring one is very unstable. One of the reasons this ring is very unstable is if we make a triangle like this, then what are the bond angles? The bond angles are all going to be 60 degrees. which is going to be highly stressed. And so rings like this are quite unstable. And so we're going to not, ozone is not like explosively unstable. So here, then what do we do when we do Lewis structures? We complete the octets to the terminal atoms first. And that takes care of 8 and 8 is 16. That gives us 2 electrons left over, except when you look at the middle oxygen, does it have an octet? No, so what we'll do is we'll strip the pair and make it a bonding pair, a lone pair off a terminal, and make it a bonding pair. And this is going to create something like this. Okay, then we look at the formal charges. Everybody has an octet now, but it's not totally happy yet because what are the formal charges? You guys remember how to do formal charges? The formal charge on this one is 2, 4, 5, 6. It's supposed to have 6, so the formal charge is 0. The formal charge on the middle one is 1, 2, and then we count half the bonding, 3, 4, 5. So it's got 5 electrons. The formal charge is plus 1. On this oxygen over here, we got 1, 2, 3, 4, 5, 6, and then half the bonding, 7, which makes it a minus charge here. And then we'll have resonance form for this. So what's happening with the ozone here is, well, this is formal charge. When we do oxidation state, it's a winner-take-all type situation, but winner-take-all, it's oxygen versus oxygen is a tie. So interestingly enough, for this molecule, the oxidation states are the same. So the oxidation states I'd like to do in parentheses here. So if I do that, this one comes out 0 oxidation state. This one comes out plus 1. This one comes out minus 1. So formal charges, what we often do is there's a little bit difference in convention here. So oxidation states, we write the number 1, so plus 1, whereas formal charge, this is plus. It's plus 1. If it's 2, then we'll write the number 2. And so the red are the oxidation states, the green are the formal charges. So let me do something here. Got to get some extra pages. So what's happening with ozone is some of the oxygens are not changing. 2 of the oxygens stay at 0. Or, yeah, actually, technically, they aren't at 0. They change because when we look at it individual, the average is 0. When we look at it individually, some changed there. In O2, both the oxygens are 0. And then in water, the oxygen's a minus 2. So one of the oxygens came out minus 2, which is isoelectronic with neon. Now, this oxygen can undergo further reaction and oxidize something, take electrons. But anyway, this was the weird disulfate kind of thing, but it's a peroxide. Normally, when you look at something like dichromate, is kind of weird, but if you know a little bit about structure, it makes a little bit more sense. So if we have like something like chromate, we think about chromate first. So if we have something like chromate, like this, and it depends on how you draw out the structure of chromate. Actually, I'm not going to do it quite yet, etc. I don't want to talk about it so much, but normally you'd think a dichromate would be something like this. You just take two of the chromates and link them together. But the problem is this linkage here. This linkage is called a peroxide bond. Peroxide bonds are very weak, therefore unstable and reactive. So what we do is we try to avoid peroxide bonds. And so that's why in dichromate, one of the oxygens is missing. So in dichromate, we have a link like this, which is fine. A chromium-oxygen-chromium link is not a problem. And so what we get is this. We get, oddly enough, if I do all the electrons, we'd see that the charge stays the same. So dichromate is Cr2O7, not Cr2O8, 2 minus. The peroxide links have a different oxidation state. When we look at the oxidation states of these oxygens, they're all -2. But when we go to this, this is a -1. This is also a -1. This is a -2. This is a -2. This is a -2. We'll talk more about how to do oxidation states from Lewis structures when we get to Lewis structures. These are all -2. That means chromium is +6. Chromium's +6 here. All these are -2. Over here, the chromiums would maintain a +6. +6 is its max. So when we look at something like this disulfate here, we take a sulfate, and there are two ways to link it. This is going to give us this. It's going to give us a peroxide bond because this, the formula for this is an S2O8, 2 minus. And so it is really linking up two sulfates, but we have this peroxide. And the peroxide, the oxidation state on oxygen in peroxide is -1. It's not quite to -2. Oxygen wants to get to -2 to be like neon. And so it's like fluorine right now with 9 electrons. Is fluorine happy with 9 electrons? No. Fluorine, neither is oxygen. Oxygen's not so happy with 9 electrons. Oxygen wants 10 electrons. And therefore, this disulfate is not, it's called a peroxide. So this is like a peroxide. And peroxides are not happy because they got 9 electrons on the oxygen. They want 10 electrons on the oxygen. However, when you do the oxidation states, we would get a very unusual oxidation state for this. I talked about this last week, did I? What was the oxidation state? Determine the oxidation state on sulfur. Well, oxygen's -2. Did you guys practice oxidation states? Or do you need more practice? You should be able to do this one in your head. If you can't, then you need more practice. There's some tutorials online to do it. +7. What's unusual about +7?
It goes up to lower, but it usually will go up to like remaining stages, so maybe like up to 10.
Yeah, what's the range of oxidation states for sulfur? The expected range.
Plus
Plus 6. +6 is the max. +6 because it has 6 valence electrons. If you lose all 6 valence electrons, then it's +6. To get to +7, that means you have to lose not a valence electron. What are the inner electrons called? You have the valence electrons, the outer shell electrons, and then you have the inner electrons. The inner electrons are called the yeah, they're called the inner shell, but there's another name for the inner shell electrons. Yeah, what are the inner shell electrons called? Remember Tanner? Rory? Yeah. The core electrons. Core electrons is what they're called. So, go +7, you gotta lose a core electron. This is very, very, very unfavorable. It costs like 10,000 times more energy to lose a core electron than a valence electron. This is unlikely to happen. And so, it's not +7. And so this is another reason why we do individual oxidation states like this. You know, to do individual oxidation states, we need the lone pairs in there. And then it's winner take all. So when I do the oxidation state, it's actually really simple. Oxygen versus sulfur, oxygen wins. It's more electronegative. Oxygen versus oxygen, it's a tie. They're both equal. And then we count the electrons. The way we count the electrons is sometimes we'll have to divide the bonding electrons. Sometimes it takes them all. And so in this particular case, oxygen versus sulfur, oxygen wins both of the bonding electrons. So that's 1, 2. And then it has lone pairs. Those belong entirely to oxygen. 3, 4, 5, 6. And then this is oxygen versus oxygen, which is a tie. We split it down the middle, 7. So oxygen ends up with 7 electrons here, and it's supposed to have 6 electrons, 6 valence electrons, and therefore it came out with an extra electron. If it comes out with an extra electron, it has an extra -1 charge. The oxidation state is the apparent charge on. Actually, the definition of oxidation state is it's the apparent charge on the atom, assuming we have 100% ionic bonding. And 100% ionic bonding means winner, the more electronegative element takes all. And so that's where we get the -1. Whereas up here, we get a -2 oxidation state on this oxygen, because if I fill in the lone pairs here, like this, and then we do a winner take all, oxygen versus sulfur, oxygen wins. It's more electronegative. And so oxygen ends up with all these electrons, all 8 of these. All 8 of these, well, it has 6 valence electrons. That means it has 2 extra electrons, and therefore it's -2. And so these are all -2. So if we do this by structure, we can get more insight into it versus average. You know, if you take the average of everything, then you don't really see the whole picture. And so eventually we're going to be doing it like this. Although this is not in the book, but you know, it's helpful for organic chemistry. So I'll talk about it now, so that maybe by the time you get to, or if you're taking organic chemistry, maybe by the time you get to organic, it makes sense. Okay. So the first thing in learning about redox is to look at electron poor. Why are these electron poor? Well, oxygen is -1. Hydrogen peroxide. Hydrogen peroxide, oxygen is -1. Here, we can use the rules and it works out fine. We do hydrogen first at +1, that means oxygen must be -1, each oxygen. So that's electron poor because it wants another electron. So what we're trying to do is we're trying to look at patterns as well. Permanganate doesn't seem electron poor because it's got an extra electron. -1 charge means there's an extra electron in there. But it depends on which atom the extra electron goes on to. You know, and so when we look at the structure of permanganate, which electron does that extra electron go to? And so it turns out that extra electron goes on to oxygen. So when we look at permanganate, MnO4 minus, the oxygen's happy as is. However, the manganese is not. What's the oxidation state on manganese? +7 is correct. Let's see. Fix this. And so it's not because it has a negative. The extra electron went onto an oxygen, and that's just to make the oxygen happy. So this is +7, the manganese. The oxygen's happy at -2. The extra electron did not go on to manganese, and so this is what manganese at +7 is maxed out. So it's going to want an electron. And when it takes electrons, it takes 5 electrons. So we drop it from +7 to what? So we're going from +7, we gain 5 electrons, we're going to take it to +2. Not all the way to 0, but it turns out manganese 2+ is fine. It's pretty stable. So it doesn't go all the way. Over here, like the peroxide goes from -1 to -2 in water. Water is very stable. The disulfate peroxo, it has a very unusual name. It's not called disulfate. It goes to 2 regular sulfates here. So the oxygens all go -2 here. Over here, so this is electron poor because of the high positive oxidation state of manganese. Over here, what's this? Not lead-2. Oxygen's -2. You have 2 of them. 2 times -2 gives us -4. That means lead must be +4. So this is lead-4 oxide. Lead-4 oxide, lead-4 is kind of a high charge. You know, there aren't that many +4 cations. Tin-4 is a bit more stable, you know, but lead-4 is kind of high. You know, most of the highest charged cations we think of are like aluminum, 3+, and iron. These, you know, of course. Here, it helps that there's oxygens. The oxygens help stabilize the charge. But anyway, we go from lead-4 to lead-2 by gaining 2 electrons. Now, fluorine is more electronegative than chlorine. So chlorine, it makes sense. Fluorine, chlorine, the halogens. We look at dichromate. Dichromate has -2 charge. Why is this electron poor? It's electron poor because of the chromium, which is in the +6 oxidation state. I just did it earlier. MnO2 is manganese 4 oxide. And so here we're going to go from manganese 4 to manganese 2 by gaining 2 electrons. Up here, permanganese was plus 7, plus 5 electrons gives us manganese 2. Oxygen. Oxygen is what gave the, oxygen is the, I guess, the prototypical oxidizer. Oxygen, of course, oxygen's around. We live in an oxidizing environment, but it's not the strongest oxidizer around. There are stronger oxidizers around than oxygen. But oxygen is a pretty decent oxidizer, too. And then we have what? Iodate. Iodate, what's the charge on iodine? I think I asked you this last week, maybe? Maybe not. Plus 5. Yeah. And so it's going to iodine, which is 0. So we have 2 iodines at plus 5. That means we're going to have to gain 10 electrons to go to iodine at 0. Bromine to bromide, nitrate, and acid. This is going to give us nitrogen in nitrate is what? Plus 5. And so we got plus 5 plus 3 electrons gives us what? Plus 5 minus 3 gives us plus 2. So nitric oxide or nitrogen monoxide is plus 2. Silver ions are good oxidizer. Silver ions, you got to watch out. If you use like silver salts can easily oxidize your skin. So if you spill silver salts on your skin, do you know what color it turns? Black. It turns black because it forms tiny crystals of silver metal. However, what happens is the silver salts penetrate your flesh, and the crystals are actually in your cells. So it doesn't wash off. Have you ever spilled silver salts on your skin? Yes, lots of times I've spilled silver salts on my skin, and you try to wash it off. It doesn't wash off. Eventually, your skin sheds. So I know I told the Chem 4 students this, but I had a student in Chem 4 spill silver salts all over, silver nitrate. It was aqueous, all over her hands. And came up to me and said, I've been washing my hands for 20 minutes and it's not coming off. I told it's not going to come off. And then the thing was she had a job interview right after class, an important job interview. Yeah. So anyway, you got to watch out. They're good oxidizer and they precipitate out silver metal. Silver metal is also known as a heavy metal, so you want to be careful. Although in this form it's not very toxic, but in this form it's more toxic. Iron 3 wants an electron to form iron 2. It doesn't go all the way to iron metal. Oxygen, well, we have oxygen again, but this oxygen's weaker. This oxygen's stronger. So whenever we have a weaker and a stronger, we pick the stronger. So why do we even bother with this weaker oxygen? Well, it's not because of oxygen, it's because of the reducer on the opposite. So we have a conjugate relationship, an oxidizer and its conjugate reducer. And so we're looking at the reducer. Here, it's hydrogen peroxide. Over here, the reducer is water. And so that's the reason you see oxygen twice. It's not because they're trying to confuse you. It's because of the conjugate. They only want to make one table. And this one table is going to be both for the oxidizer and reducer. So if we go back to fluorine here, fluorine has 9 electrons, it wants 10. Now it's got 10, it doesn't want to give those up. So it's like neon. So this is very stable. So if the oxidizer is very reactive, high energy, then its conjugate reducer is going to be low energy, very stable. So fluoride is very stable compared to fluorine. This is the conjugate relationship. In other words, it wants 2 electrons, and once it has it, it doesn't give them up. Okay, below oxygen we have iodine. Iodine, yeah, it makes sense. Fluorine, chlorine, iodine. Iodine is bigger, it's not going to be as reactive. as bromine. Did I skip bromine? No, I didn't. Bromine was up there. Now I remember. Iodine. Copper 2 goes to copper metal. Sulfate in acid goes to sulfur dioxide. Sulfate's +6. Sulfur or sulfur dioxide is +4. Tin 4. It's unusual to see a monatomic ion, no oxygen there. It's not a polyatomic ion with a +4 charge. Goes to tin 2. Sulfur. Sulfur is not nearly as powerful as oxygen. And sulfur doesn't form diatomic molecules either. And so sulfur goes to -2 in hydrogen sulfide by gaining 2 electrons. H+, acid, is a pretty good oxidizer. Acid is like a mid-range oxidizer. Lead 2, tin 2, iron 2, zinc 2, all these metal cations can be what we call reduced to the metal by oxidizing something, taking electrons. The worst oxidizer on this chart is lithium ion. Lithium ion is the weakest of all the oxidizers. It takes an electron, forms lithium metal. So if we have a very weak oxidizer, lithium ion, then its conjugate must be very strong. In other words, lithium ion doesn't really want an electron. Therefore, lithium metal can easily get rid of that electron, so it makes a very powerful reducer. So lithium is a very powerful reducer. Lithium ion is a very weak oxidizer. So this is the conjugate. It's a seesaw relationship. If one side's high, the other side's low, vice versa. Now these ones are in a separate table here, but we can rank these by looking at the number on the right. These numbers on the right we use in Chem 1B. But for Chem 1A, we're just going to rank the relative order. And so water is not at the bottom. Water is not the weakest oxidizer. Where's water positioned? Well, I drew these 3 dots here. The 3 dots are meant, that's where water goes. Water goes here. Water is very important in analyzing chemical reactions. So we'll throw it there. Okay, let's start off with the reducers, going from the strongest. There's some others. These are basic. So we see ozone again. Hypochlorite is there. The reason they put it in a separate table is because these ones often require acid. These ones require basic solutions. And so hypochlorite's bleach. Bleach is a good oxidizer. Where do we position bleach as an oxidizer? You know, a lot of people bleach their clothes, bleach a whole bunch of other things. I saw some bleach art. So there's somebody making bleach art by taking black cloth and using bleach to put drawings and stuff. Minus or plus 0.89. Plus 0.89. So bleach is stronger than silver ions, but weaker than nitric acid or nitrate and acid. And so bleach falls in right about here, at 0.89. And then we have oxygen in base, we call it basic solution, and water. All right, so let's go down the list of reducers. Now, a lot of these are the alkali metals. The things on the far left end up losing their electrons easily. So lithium is the best, potassium, calcium, sodium. Lithium is the best, but it's not the most reactive. Out of this list, potassium is the most reactive. Potassium is the biggest atoms, easy to oxidize. So those can react violently. It's not to say lithium can't. Lithium battery fires are... I guess there was a lithium battery fire on the... They said it was on the St. Vincent Thomas Bridge, but I guess it was off the bridge, wasn't it? Yeah. Well, anyway, that's there's some kind of storage device there. So we got to watch out. These ones are powerful reducers. And then we have the group 2, and then group 3, aluminum, and then we have the pseudo group 2, zinc, and then iron, transition metal, tin, lead. All these are good. reducer. It's better than hydrogen gas. Hydrogen gas is known as an excellent reducer. These are fuels. The fuels supply the electrons. So what we do is we look at these. When we have lithium react, we have to reverse this equation. So we rewrite this equation backwards. So lithium goes to lithium ion plus an electron. And then hydrogen. Sulfides are pretty good. It's unlike water. I mean, this is kind of like water, H2O, except sulfides give the electrons a lot easier than water does. Water is a lot harder to oxidize than hydrogen sulfide. Tin 2 can go to tin 4. Sulfur dioxide can go to sulfate. Copper can go to copper 2. Iodide can go to iodine. Hydrogen peroxide can go to oxygen. All these give up electrons. Iron 2 goes to iron 3, giving up an electron. Silver goes to silver ions, giving up an electron. Nitric oxide can go to nitrate, giving up 3 electrons here. Bromide. And it's getting increasingly difficult to take electrons from these. Iodine, water. Water is pretty hard to take electrons from. Here. Manganese 2 to manganese 4, chromium 3 to chromium 6, chloride, lead 2. The hardest to take the electrons from would be fluoride here. So this is some oxidizers and reducers. So we're going to look at some oxidizers and reducers in lab today. So let's take a look. Do you know what was the experiment number? 18? 17? Well, we did 17 last week, kind of. We didn't finish it. What's the next one after 17? 18? Okay. 18, we're going to look at redox reactions here. We have metals. Metals are good reducers. Out of these three, which one do you think is the best? Most reactive? Which one do you think is the most stable out of those three? What would you rather? Would you? Need some tweezers. What do you think is the best? I mean, for jewelry. Would you want lead jewelry, copper jewelry, or zinc? Zinc? You know what they use zinc for? They use zinc to coat nails. Do you know why they use zinc to coat nails? It's called galvanized. They use zinc to coat lots of iron products. It's called galvanized iron. You know why they use zinc?
So that because it doesn't oxidize?
Yeah, they use zinc to protect the iron. The zinc corrodes a lot easier than iron does, and so that's to protect it. You know, they used to use lead pipes. Lead pipes were used because they'd form an oxide coating, which was pretty unreactive, like lead sulfate. So the most stable of those three metals is copper. So this is going to be the least reactive of the metals. The most reactive of those three will be zinc. Lead will be somewhere in between. We could see this on the redox chart as well. Copper is the least reactive. It's farthest away from lithium. And then there's lead, and there's zinc. Zinc is the closest to lithium. So zinc's the most reactive, then lead, then copper. Lead is a heavy metal. We don't want to touch it with our fingers. You could use some tweezers to touch it. Now, lead is going to have a black coating. Do you see it? It's kind of hard to see, but it's it's whereas zinc is going to have a silver, like a dull silver appearance. Do you see that? And so zinc is going to have, lead is going to look black, zinc is going to look silver, and then copper, of course, looks like copper. Don't sand these. It tells you to sand them, don't sand them. Especially the lead. You don't want to sand the lead because you're going to create lead dust, and the lead dust is going to get in your skin and contaminate yourself. In fact, maybe we'll skip the lead. You want to skip the lead? Yeah. Let's skip the lead. Just react the copper and the zinc. That should be good. So skip the lead. Yeah, I prefer that. So all we're going to do is we're going to see this. We're going to see, we're going to take some zinc metal and mix it with some copper 2 sulfate. Now, copper 2 sulfate, you should know copper 2 ions. Copper 2 ions are a what? Copper 2 ions are an oxidizer. And what about sulfate? Sulfate's also an oxidizer. What's a stronger oxidizer, copper 2 or sulfate? Copper 2. So it's going to be the copper 2 that's going to try to attack the zinc. Is copper 2 going to be strong enough to attack the zinc? And the answer is yes. So the way we can use this chart is the zigzag pattern. So if we have copper 2 attacking the zinc down here, what forms? So this is the zig, and then we look at the zag. What forms is zinc ion. And we're going from a stronger oxidizer to a weaker oxidizer. Therefore, we predict reaction should occur. That's a zigzag pattern. So for sure, I should see a reaction here. And what's going to happen is I'm going to form copper metal. This is the other zag. We have 2 zags, so the zig, zag, zag. And so we're going to eat up the zinc, form zinc ion, and then deposit copper metal. Copper metal in tiny crystals looks like silver metal in tiny crystals, black. And so you're going to build a black furry coating on the zinc. As the black furry coating grows, as the crystals grow, they look silver. So you just let it sit in the test tube for a while, and then it'll look silver.
Is there any chance you could write the reaction on the board?
Can I write the reaction on the board? I could, but let's just, all we're going to do is we're going to take observations today. And so, you know, you're going to write the reactions too. I just don't want to take too much time talking. So I want to stop talking shortly. Let me write the more complicated ones on the board, though. Where did it go? So what we do here is this. We just put a couple of squirts. You know, there's going to be a little plastic pipette. One squirt of the pipette is about 1 milliliter. So just put 1 or 2 squirts of copper 2 sulfate in with your zinc metal. Put your zinc metal in the test tube like this. couple of squirts of copper 2 sulfate, and then just let it sit. Let the crystals grow. Okay. The same thing goes for all these others. Actually, let's cancel out the lead. You know, we're not going to do the lead metal. We're not going to do the lead. This is wrong, by the way. 0.1 molar. This is not supposed to be lead 2 sulfate. Cross that out. That's supposed to be lead 2 nitrate or something. Lead 2 sulfate's an insoluble solid. It's not going to form a solution that's 0.1 molar. And so that was a mistake. I thought that got fixed, but it wasn't fixed. But nonetheless, we're not going to use it. So I don't want people spilling lead 2 nitrate all over their hands in a rush. Unfortunately, this is, I'm going to have you use the silver though. But here you can tell if you spill it all over your hands. You know. But still wash your hands even though it's not going to wash off. So we're going to use silver, which is a pretty good oxidizer, and then we're going to use HCl, which is also a good oxidizer. Now, when we compare silver and nitrate, which one's a stronger oxidizer? So let's take a look at silver ions versus nitrate. If we look at silver ions versus nitrate, which one's stronger? Nitrate. So you expect the nitrate to attack. However, nitrate's not going to attack here because there's a key ingredient missing. What's the key ingredient that's missing? Acid. There's no acid. Nitrate needs acid. Does silver ion need acid? No. And so this is, all we're doing is we're taking silver nitrate plus zinc. If you take silver nitrate plus zinc, there's no acid. If we're missing this, this is like, you want to make some cookies. If you want to make some cookies, you need 4 cups of flour and 1 cup of sugar. Let's say I'm missing the flour and all I have is sugar. Can you make cookies just from sugar alone? No, it's not going to work. So this is the same thing. If you're missing this key ingredient, it's not going to be nearly as effective. It could oxidize, but its strength is significantly weakened. And the pattern goes here. Why do we need this? Why we need this is because the oxygen's here. We need it to stabilize it. Otherwise, what we end up with over here is oxide. Oxide, what do you know about oxide? Oxide's too powerful of a base to exist in water. And so in order to stabilize it, it needs hydrogen from somewhere. And best would be from acid to make water here. And so we have 4 H pluses. We're going to make 2 H2Os. And so 2 of the 3 oxygens and nitrate go to water. Yes?
So using the zigzag method, is it like nitric acid reacting with solid silver, making the silver ion? And like
yeah, the zigzag method. Zigzag method will work here. Silver is hard to dissolve. You cannot use normal acid to dissolve silver. Let me show you. This is normal acid here. This is what we call a mineral acid, like HCl. HCl is a normal acid because the chloride doesn't do anything. It's just the H+. So if I use normal acid to try to dissolve silver, here's my zig, and then I look at my zag, I form silver ion. So I'm going from H+ to silver ion. Is that going uphill or is that going downhill? That's going uphill. That's not favorable. And therefore, we do not expect silver to dissolve in normal acid. However, if we try to dissolve silver in nitric acid, it works. Because nitrate and H+ makes nitric acid. So here's our zig, and then we look at our zag here. Are we going downhill? We're going downhill here. So nitric acid will work to dissolve silver to make silver ions. So don't use nitric acid on silver coins or jewelry or whatever else because it will dissolve it.
will it still make water and
Yeah, it'll make all the other stuff as well. Okay, let's move on to some of the other reactions here. Now, this is, we're going to do these here. this is kind of a weird reaction. So we're going to take potassium chloride and bromine water, and potassium chloride and iodine water, and potassium bromide in these. So we're going to do these reactions here. These we're going to do in the test tube. And so let me try to draw it out, what we're trying to do here with these reactions. CHCl3 is called chloroform. And chloroform is like oil, but unlike oil, it sinks. Chloroform is very dense. It has those heavy chlorines on there. And so it sinks in water. And we're just going to put a drop or two of chloroform. Don't put in too much chloroform because the colors don't come out as nice. The less chloroform you use, the nicer colors you're going to get in this particular experiment. So let me do one with a reaction here. I'm going to do potassium iodide. Don't measure any of these out. So all I'm going to do is I'm going to put 1 squirt of potassium iodide in here, or 2 squirts. 1 or 2 squirts of potassium iodide aqueous. And then that would be about 1 or 2 milliliters. Other people have other ways of measuring a milliliter. Some people say it's a thumbnail's height in a test tube is a milliliter. Other people do 20 drops. 20 drops is a milliliter. I just do a squirt or 2. And then what we're going to do is we're going to add some drops. You know, I'd add between 2 to 5 drops of chloroform. CHCl3. What's going to happen is that chloroform is going to sink to the bottom. And you'll have a little bubble of chloroform down here. It's a CCl. Do you know what CCl stands for? Clear colorless liquid. All right, then we're going to add some, what is this here, potassium iodide. I'm going to add some chlorine water to this. I'd probably do 1 mil, 1 squirt, 1 squirt. If you do 2 mils and 2 mils, it's getting too much, but it doesn't matter. Whatever you feel like is fine. And then we're going to stopper this and mix. When you stopper this, be careful because you don't want chloroform all over your finger. So you got to make a tight fitting stopper here. And so this is what's going to happen. What's going to happen is we're going to have 2 iodides react with chlorine to form iodine plus 2 chlorides. Here. And then what we're going to do is we're going to do something called a solvent extraction. We're going to mix this with chloroform. And so right now this is iodine aqueous. Iodine aqueous is kind of a light purple. But iodine much prefers chloroform over water. So what we're trying to do is we're trying to extract the iodine from the aqueous layer to the chloroform layer. This is called solvent extraction. And if we don't use too much chloroform, then this should come out bright purple. And so the first thing is we're going to see what colors these come out to. And so chlorine aqueous is a light yellow to colorless. But if we do a chloroform extraction, this is the first series of test tubes. The first series of test tubes are just only extraction, not reaction. So this comes out bright yellow. Chlorine in chloroform. So these are just your reference colors. Control group. Bromine in chloroform gives a bright orange. So you have to shake it up. It forms an emulsion and then it extracts. It takes the bromine out of the water and it concentrates it into the chloroform. And iodine gives the bright purple. So you can tell if no reaction occurred. If no reaction occurs, then, you know, there's no color change, basically. You know, it stays yellow, whether light or bright. Or you can tell if a reaction occurred. You know, there's going to be a color change. In this case, there's a color change. You know, because we went from light yellow, here, and then iodide in water is just a very light. Iodide is actually colorless. Iodine is light purple. So there's going to be a color change. So that's what you're looking for here. All right, any questions on this? Just make sure the stopper is well sealed. And you got to watch out because it can generate a little bit of pressure, which tends to pop off the top. You know, when you shake organics, volatilizes a little bit, creates a little bit of pressure. So be careful, you know, when you handle this. Chloroform is something you don't want on your hands. All right, then we're looking at some other reactions here. So here's the control, and then here are the reactions. Then we're going to look at iron 3. Will iron 3 oxidize potassium or bromide or water? I probably should write this on the board. So we're going to react iron 3 and bromide. So will it react? Iron 3 and bromide, will that react? No. We don't expect any reaction here because that would be uphill, right? But what if we take iron 3 and react it with iodide? Will that react? Yes, iron 3 and iodide should react. So let's take a look at the lab here. And so if I take iron 3 and bromide, I'm not going to expect it to react. And the chloroform layer is, if iron 3 and bromide react, I should form bromine, but bromine's uphill. And so I'm not going to see the bright orange here. But if I take iron 3 and iodide, I expect a reaction. So I should see a purple chloroform layer here, because iodide is going to be converted into iodine. Permanganate's a powerful oxidizer. You know, one of the more powerful oxidizers. You should know the chart here enough that you can tell. You have the strong oxidizers up here, the moderate oxidizers in the middle, and the weak oxidizers on the bottom here. Permanganate's on the stronger end of the spectrum here. It's ranked, at least on this chart, it's ranked 1, 2, 3, 4, 5. It's the 5th most powerful oxidizer on this chart. And so we're going to take permanganate and react it with HCl. When we take permanganate and react it with HCl, we're going to see if we can oxidize the chloride in HCl. So will permanganate oxidize the chloride in HCl? Yes. And what should we form? Chlorine. So this is downhill. We're going to take permanganate, react it with the chloride to form chlorine. And chlorine in chloroform should look bright yellow, you know, if you shake it enough and extract it all. But it's a gas, so watch out for the pressure building up in the test tube. It can pop off the lid and spill chloroform all over your hands and permanganate. You don't want to get it all over your hands. But we need it. What ingredient do we need also? So if this is sugar, then we need how many cups of flour? 8. But we'll have plenty because we're reacting not with just chloride, we're reacting with hydrochloric acid. Hydrochloric acid has plenty of H+, so we're fine.
Wait, where's the hydrochloric acid?
I'm sorry?
Where's the hydrochloric acid?
Oh, we're taking permanganate and reacting with hydrochloric acid. Now the permanganate that we're reacting is going to be solid potassium permanganate, which is purple crystals. Don't touch them. But they're purple crystals, so it's very concentrated. This is a classic reaction. This is to generate fresh chlorine gas. This reaction is used as a source of chlorine. You know, you can buy a tank of chlorine, but it's expensive, and you got to store it. So if you want some chlorine gas, you can make it pretty easily, just by taking some solid potassium permanganate and mixing it with hydrochloric acid. And the permanganate is going to attack the chloride. The next reaction is copper and bromine. Here. So we're going to just take some copper metal and mix it with bromine. And actually, I think we're going to take copper wire. Do we have any? I don't know if we have any. And when we look at the procedure here, I should have had you prep the procedure. We might not have the copper metal turnings. We might have a water bath prepared in the hood, as you did for the KMNO4. You got to do the KMNO4 in the hood. It generates chlorine. We don't want to breathe the chlorine in the lab. So the hood is going to collect all the chlorine gas that's generated in the previous reaction. So you're going to do this in the hood. Actually, we're not going to make a water bath. The potassium permanganate doesn't need it. So we're just going to do it. In your largest test tube, place some copper metal turnings. This is this like copper wire kind of thing, fiber, to about 20% of the height. The turnings should be loosely packed. Don't pack them down in there. They're sharp, so avoid cuts. So we just get some scissors and cut the copper turnings. Hold the test tube with a test tube clamp or an empty beaker. So we could use a clamp. The beaker, at least you don't have to hold it all the time. So you could use a beaker. And then add some bromine water to cover all the copper. This one you might need a little bit of heat. I think it works a little bit better with the heat. And if I'm going to heat it up, I could just heat it up with a Bunsen burner. When you heat it up with a Bunsen burner, just heat it on the soft part, not at the tip of the cone. That's way too hot. Don't point it at yourself, you know, because it could splatter into your face. Point it away from everybody. Yeah, don't point it at your neighbor either. And then just gently heat it. What's going to happen is the bromine water, it will go from orange to colorless to blue. You know, the more so what we're looking for is the bromine water should go from orange to colorless to blue, but the blue could be very faint. And so just keep heating it. Sometimes it's hard to see the blue. The blue is from copper 2+. And so what we're going to do is we're going to test it for copper 2 plus. There are two ways we can test it here. Actually, sorry, there's one way we can test it. The confirmatory test for copper 2 is the formation of deep blue complex when you add 6 molar ammonia. Sometimes the blue is super faint. And so what we're going to do is we're going to divide the solution here into 2 test tubes. Test tube 1, we're going to test for copper 2. Test tube 2, we're going to test for bromide. So the test for copper 2 is to bring out that blue color, we add aqueous ammonia. When you add aqueous ammonia, the color just darkens to deep blue. If we see a deep blue, then that means we have copper 2 ions present. And then to the other test tube, so you're going to divide this into 2 test tubes. The other test tube, we're just going to add silver nitrate. When we add silver nitrate, we get a precipitate of silver bromide. And so we're just testing for the presence of copper 2 and bromide, because in this particular reaction, that's what we expect to form here. So let's go back to the reaction quickly here. So if I take bromine and react it with copper, that's my zig, and the zag is going to form copper 2. We're going to test that with aqueous ammonia. You might see it. You might see a faint blue color. But to really confirm the presence of copper 2, we need to add some aqueous ammonia. And then the other product here is bromide. So that's the other zag. The bromide we're going to test with silver nitrate to form silver bromide. All right, and the final reaction we're going to do is this one here. Silver and iron 2 ions. So we're going to take silver ions and iron 2 ions. When we take silver and iron 2, let's take a look at what potentially could form here. It's silver nitrate and iron 2 sulfate. However, we're missing acid. And so we're taking silver nitrate. Nitrate's better, but we don't have any acid. If we don't have any acid, then that drops its rank, so silver ion is going to be the best. It's better than iron 2. Where's iron 2? Here. Iron 2 is way down here. So the best is nitrate, but we're missing acid, so it doesn't work. The next best is silver ions. The worst oxidizer would be iron 2. But iron 2 is weird, because iron 2 occurs on both sides of this chart. Do you see iron 2 here? So iron 2 can either be an oxidizer or it could be a reducer. And so let's see what the best reducer we have is. We have water versus iron 2. Which one's better, water or iron 2? So here's water, here's iron 2. Iron 2 is stronger. And so what we're going to do is we're going to pick the strongest oxidizer, iron 3, and, well, not iron 3, what are we doing? Silver, and the best reducer, iron 2. So is this going to be favorable? This is my zig. So iron 2 reacts with the silver to form iron 3. We're going down. Therefore, we expect reaction here. And so what's going to happen is the silver ions will react with that. However, there's competing metathesis reaction in this particular one, and that is silver sulfate precipitate. So what you might see is the metathesis reaction occur first. A white PPT is silver sulfate. And then after a while, that white PPT should turn black with silver metal. All right, I'm going to stop here. So the main thing is the observations. We're going to do the reactions later. So
we're not sanding the metals?
Do not sand the metals. If you don't sand the metals, it's going to take more time, so let them sit. If you don't see a reaction occur right away, just let it sit for a while and move on to another set of reactions. You could do this in any order, so you don't all have to pile onto the metals. The metals are located at the hood over here. Again, you can work in a group of 1, 2, or 3. And what we want to do is we want to take observations. So take observations. Color changes, precipitate formation, etc. Gas formation. All the chemicals are located in the hoods over there. Some of the reactions do in the hood. Anything that generates like chlorine or anything hazardous do in the hood.